Let's build the framework to put pixels on the screen. Warm up the CRT, it's time for another episode. In the last two videos, we built the basics to lock our NTSC composite signal to the monitor. Now we have to generate the timing required to make pixels. But before we do that, I'd like to go over a change I made to the vertical blank and vertical sync signals. Every time I go over this design, I find new ways to make it simpler, and that's part of the whole design and learning process. I wanted to let you in on all of that without trying to hide it behind movie magic. So let's review. In the last video, I stated that vertical blank runs from line 1 to line 21, but I used line 16 as the endpoint instead for selection simplicity. I realized that if I went ahead and made the endpoint 21, it would eliminate future redundancy in my design. I start by popping the existing 74LS20 with 16V, 4V, and 1V to make 21V. I also pull one of those inputs twice to ensure the extra input isn't floating. Then I use a spare gate on the existing 74LS02 to invert it to make the new set condition. This makes the new V-blank and not V-blank signals that start at 0V and end at 21V. This creates a problem for not V-sync. If we know our binary math, we know that the 4V line goes high again at 20V, which means we will get a little glitch. We can take that signal into a 74LS32 OR chip along with 16V to negate off the glitch, and this gives us the correct not V-sync signal again. So if you're building along with me, take a moment to fix that up now. Now let's get to generating new signals. These signals are Pixel Enable, a reference that lets us know when it's safe to make pixels. Pixel Clock, a reference that tells the pixel generator when to output the next pixel. 3.58 MHz subcarrier reference, the master color reference frequency. And Color Burst, a short shot of the color subcarrier to tell the TV we intend to make color. Here's what you'll need for this phase of the project. The previous work and power supply. The 74LS32 chip we added to fix V-blank. Two 74LS74 dual-unit D-type flip-flop chips. One 74LS02 quad-unit NOR chip. One 74LS20 dual-unit quad-input NAND chip. Another solderless breadboard, and connecting wires. The first signal we need is the Pixel Enable signal. This signal is used later as a chip enable reference. It helps us ensure that active video output is generated only during visible lines, and then only when horizontal timing isn't happening. It's generated by pulling V-blank and H-blank into the 74LS32 OR I added before to give us not PixN. Let's build it. This one's easy. We bring in H-blank, and then V-blank. Let's show it on the scope. Next, we need to build the pixel clock. The pixel clock tells the future pixel generator logic exactly when to fetch the next pixel from memory. Pixel clocks should be an even ratio to the color subcarrier. This ensures that when the pixels hit the screen, they hit in relative phase with the color burst to prevent interference patterns. This is where we have some fun, determining how many pixels to fit into a line. How do we do that? Well, first, we need a frequency that's some divisor of 14.31818 MHz. And second, we want a number of pixels that fits within a single byte, that is, 256 or less. So let's do the math. We can only generate video during the active video area, basically during not PixN. This is 52.66 microseconds long, according to spec. If we divide that by 256, we get 0.206 microseconds. The closest pixel clock to that value, that is also a division of the 14 MHz clock, is 4.77 MHz. That's 14 MHz divided by 3, giving a period of 0.21 microseconds. That fits into 52.66 microseconds, about 251 times. Close enough. Now we have to divide by 3 using logic. Not as easy as dividing by 2, but definitely doable. We do it by using a pair of 74LS74 D-type flip-flops chained together through a NOR gate. What is a D-type flip-flop? Well, it's basically a single unit memory cell. Whatever data is presented on the D input when the clock goes high is then presented on the Q and not Q outputs when the clock goes low. Q is equal to the D input, and not Q is the inverse. So here's what our circuit looks like. Basically, the half-clock offset of the Q outputs of each of the counters combines into the NOR to give us a signal that is high for 1 clock cycle, but low for 2. To start, we tie the not clear input of Unit 1 to not H reset. This ensures that the pixel clock always starts in lockstep with the beginning of each line. Then, the remaining clear and preset inputs are tied high. Remember, no floating inputs. Both units' clocks are fed with 14 MHz. The Unit 1Q is fed into the Unit 2D input. The Unit 2Q goes into a free gate on the 74LS02. The Unit 1Q output feeds into the other free input. Then the 74LS02's output goes back into Unit 1D as feedback. This gives a 4.77 MHz signal on all D, Q, and not Q lines. They have slightly differing phases, and I can pick whichever one I want to fit my taste in color fringing artifacts. In case you're wondering, this clock creates 33% duty cycles. I can add a chip or two and rearrange a bunch of stuff to get a 50% duty cycle, but it's not really needed for this application. It's the negative going pulses that matter. Now we need to ensure that the pixel clock is only running during active lines. We do that by combining the output with not pix in into a 74LS02 NOR gate. This gives us our final pixel clock. So let's build it. Let's get the 74LS74 and 74LS02 chips populated, and then hook them up to power. And then we tie not H reset into 1 clear to sync the circuit to line boundaries. Next, I tie the extra clear and preset lines high. Now I bring the 14 MHz clock into 1 flip-flop. Then I cross-connect the flip-flops on the clock lines and hook 1Q to 2D. Let's connect 2Q into the 74LS02 and then do the same for 1Q. Now, 1D is tied to the output of the 74LS02. Next, we have to take pix in into the 74LS02, along with the 4.77 MHz output of the first stage. This gives us the final pixel clock. Let's look at all of the outputs on the scope. Now let's assemble the 3.58 MHz reference signal. The 3.58 MHz subcarrier reference is used to generate all of the color signals we'll need later. We have to get our 3.58 MHz source from somewhere, and you may be thinking we can tap it straight off of pin 7 of the horizontal counter, since that's 1/4 of the 14 MHz main clock. But not so fast. That's a trap for young players. If you remember back to episode 1, each line is 227 1/2 3.58 MHz clocks long. So at the end of each line, we're resetting the horizontal counter on half clock boundaries. Therefore, the counter always starts at 0, and the pin 7 output is always synchronized to the counter. Now, the spec says the 3.58 MHz clock is free running. This means that every line's color burst is 180 degrees out of phase with the previous line. If we tap off pin 7, we lose that phasing. This is a minor detail, but an important one that affects the quality of the final video output. Therefore, we have to make a free-running 3.58 MHz clock. We do this by using a 74LS74 as a crude counter to divide the master 14 MHz clock by 4. You can really use any kind of divider you like. I'm using this because it's cheap and because it's good to practice using the same chip in different scenarios. Here's how a D-type flip-flop frequency divider is made. The first flip-flop gets the main 14 MHz clock into its clock input. The not Q output goes into that D input. This gives an output on Q that is exactly 1/2 of the input clock. We can then pull that Q into the clock of another flip-flop set up the same way and divide it by 2 again. So let's build it. First, we bring the 14 MHz clock into the clock line of the first flip-flop. Then we connect one D to one not Q. Next, we connect one Q to 2 clock. Then we hook 2D to 2 not Q. I forgot to show pull-ups on the clear and preset lines. Don't forget those. And the 2Q output is our 3.58 MHz reference signal. Let's look at it on the scope compared to pin 7 from the horizontal counter. You can see that the phase changes relative to the free-running clock at line boundaries. With our reference signal built, now we need to make the actual color burst signal. The color burst is a short shot of the color subcarrier signal we just generated, injected between horizontal sync and the active video area. It is used by the TV to synchronize its color oscillator to ours. This ensures that what the video generator thinks is a particular color is the same as what the TV shows. If this burst is not present, the TV will assume that we are transmitting an old-fashioned monochrome signal and it won't show any colors. According to spec, color burst happens during the back porch area of the signal at 6.8 microseconds. It is 8 to 10 cycles of the 3.58 MHz signal and is only generated during active lines. As long as it's close, though, it's not crucial. So let's do a lot of math. One tick of the 14.31818 MHz horizontal clock is 0.0698 and so forth microseconds long. So if we multiply that by 6.8 microseconds, we get 97.36 so microseconds. So that means our start number should be around 97H. 8 to 10 cycles of 3.58 MHz would be 32 to 40 horizontal clocks. If we take 97 and add 32 to 40, we get 129 to 137. Now 97 and 129 are messy. Let's pick some numbers that are easy in binary. So let's start at 96, which is 64 plus 32, and we can end right at 128. That gives us 31 cycles of H, which is 7.75 cycles of color burst. But we have a little extra bonus due to binary math. The combination of 64 and 32 together will stay high the entire time needed, and both go low the moment 128 triggers. As long as I use a couple extra conditions, it won't trigger again as well. This means I can use the combination of these two inputs as our entire selection signal. We just need to ensure it only runs during the horizontal blank period by tying in H blank, and only runs during active video lines by tying in not V blank. We pull all four of those, 64, 32, H blank, and not V blank, into a 74LS20 NAND gate to get our desired signal, called B porch, for back porch. Next, I pull that into the 74LS02 NOR, along with 3.58 MHz, which gives me the color burst reference signal. So let's build it. First, set up another 74LS20 just like we've done before. I forgot to record that part. Now, bring in 64H, then bring in 32H. Next, we bring in not V blank. Now, we bring in H blank. Take the output of the NAND into the 74LS02, and finally, bring in 3.58 MHz, which gives me the color burst signal. Let's look at it on the scope. With this phase of the project done, we have all of the timing we need to lock a signal to the screen and clock pixels. All we have to do now is connect it to a frame buffer and pixel generator, and we're in business. But that's for the next video. Thanks for watching. Remember to like, subscribe, and ring the bell to stay up to date on my latest adventures. You can also support the museum through Patreon or by snagging some merch. Links in the description. Well, that's all for today's episode. While you're here, check out some of my other videos, and remember, 8 bits are all you need. All we have to do now is connect it to a frame buffer and pixel jailer. Jainer? Jainer, a pixel jainer?